Hello everyone. In today's video, we are going to cover a very important part related to the end-to-end user plane data flow. And it will be a very interesting video. I will be trying to cover this into 2 or 3 videos because we'll be mainly focusing into the radio protocol stacks. For example, the BDCB MAC RLC layer, like the layer 2. But also I will be adding a part related to the TCP just to see what kind of interaction or consideration you need to know whenever you do any tuning within the RAN or the BDCP MAC RLC related parameters as well. So I will give also a good information about the CB for your information. So I will split into 3 videos. The first video, which will be starting today, it will be about the first part, a very high level about the end-to-end flow for the user plane. Then after we cover the architecture, we'll go through how the data is being transferred from the end-to-end perspective, and we'll show the steps and the requirements. Then I will just go quickly through the overall parameters, 3GPP, timers and parameters, configurable parameters, which can be tuned, and you will find it in any of the networks for sure. I'll just give you a quick also overview before jumping to the details, which will require a lot of visualization, especially for the TCP, BDCP, and MAC and RLC. But the first part I'm going to cover today is related to the RLC layer and with some interaction related to the MAC. The MAC will be covered in a separate session, and TCP, BDCP also will be one separate session. So we'll have 3 sessions, one for the RLC dedicated and this about 3 parts. Then we'll move to the TCP, BDCP, then we'll be ending by the MAC layer. And also all over these sessions, I will be highlighting what kind of interaction consideration you would like to know before trying to tune in with these parameters. So now let's move forward to see what we have today. So as you can see from this figure, this is the user plane overview, like for standalone and non-standalone. And as written in the top left here, the user plane in general protocol stack is responsible for transferring the application data. For example, if you have application data at the user side and the application data in general, and you would like to transfer it between the end user and the application server, here is the application server and here is the user. So this is the user plane is responsible for transferring the data from to UE and the application server. This is a first responsibility for that. And the application layer, which is the one on the very top right, is doing that through multiple other lower layers, which is including the TCP IP, and this will be explained in the very details in the upcoming slides as well. And just the important part that the application layer decide what kind of transport. Transport means the data will be transferred through which transport layer based on the services. For example, as you can see in the bottom left table here, if you have HTTP service, so for example, you're doing web browsing or internet browsing, so this need to use a TCP because TCP is like a reliable protocol, which is ensure that a less packet loss. Because at the end we need to have, as you know, HTTP or the file transfer require a very low packet losses. And so this one, for example, once we do HTTP browsing, so the application layer will know that it needs to use a TCP. And for example, the HTTP, this will be communicated through a particular port. For example, HTTP using port 80, FTP using port 21, and you have other services related to, for example, the RTP, which is related to the audio and video. This is using UDP. So this is how the application layer will know. So we'll cover this in details in the next slides, but the part I would like to cover, because as a highlight from high level perspective, because this will not be covered in the next slides, it's related to the part in between here, between the anchor or the UBF layer and JUnit-B and the IP layer in general, starting from the IP layer, tell the UBF and JUnit-B how the IP packets is being transferred. From the high level perspective, the IP packets actually will be transferred through something called GTPU. Okay, this GTPU, it's like a protocol called GPRS tunnel endpoint. This protocol encapsulates the IP packets which is coming from the IP layer and creates a tunnel between the IP network and the IP network and between the UBF user plane function. This creates a tunnel between both of them, and this tunnel ensures, the tunnel created by the GTPU ensures that the user data is delivered to the correct BDU session and quality of service in the 5G core network. This is what is the GTPU tunnel do. Then what it will do, the GTPU tunnel encapsulated packets which is being sent from the end are then forwarded over the N3 interface from the UBF. It will be forwarded through the N3 interface, which connects the IP network to the UBF, and the UBF is the 5G, how say it, the first entry of the 5G core network. So in simpler terms, the IP packets are transferred through a GPU. Okay, the IP packets is transferred through a GPU, uses a UDP protocol. This is a transport layer for UDP. GTP using UDP because actually it requires a very low latency, and the retransformation or any problems in the packets will be handled by the other layers. This will be explained in detail. So it doesn't require any mechanism to secure there is no, for example, packet losses or retransmission and so on, because this will be handled by the other protocols. So in general, this combination ensures that you have a fast, efficient, and session-specific data transfer within the mobile network. And just if you look into this part, this is just, you can just take snapshot from here. This is just summarizing each of those layers, application, TCP, IP, and GTPU, um, rule, context, and why it's being used here and there. Last point here in this slide I would like to address here, that this is the user plane. The control plane is very simple. As you can see here, and just on top of the BDCB, you will have the RRC layer. We have here the SDAP, is the AAP layer. This is used usually in 5G standalone only. We'll be explaining this part in the next slide. But the main difference is that you, for the protocol instead of user plane protocol, you'll be using the RRC. So let's move now to the interesting part in next session, in next slides. So as you can see in this slide, actually, this is will be covering the high level part, also related to how the data is being transferred. As you can see here, I summarized it into 10 points, but actually it's even more. But let's take it slowly one by one to understand what we have. For example, from the end-to-end perspective, the first thing will happen whenever you as a user, you are trying to do, for example, a web browsing, right? Let's assume you are taking example as highlighted here. This is the architecture we have. I'm giving an example here about the HTTP that the user is trying to download a web page. Okay, and here I assumed that the BTS or Jejin will be using CU and U high layer split architecture, where the DU General B is hosting the RLC, MAC, and physical, and the centralized unit is hosting the SDAP and BDCP layer. This is as a high level point of view. So how this end-to-end call flow will be happening. So application, as you mentioned here, assume the user is trying to download a web page. So what the first thing we'll do that it will be sending HTTP GET command towards the application server. So this is will be the first step. Then the application server will know that the user is trying to download a web page, so he's using the HTTP. So in this case, the data which is in the application will be transferred through the transport or the TCP transport protocol, because again, transport TCP is used for HTTP as we highlighted in the previous slide, and the reason for that, it requires a very high reliability, that you require a very packet loss, because at the end you cannot download a page or a file where it's having a lot of packet losses, right? At the end, you cannot see all the content, so right? It's not something related to the video streaming or, for example, the audio calls and so on. So the application here will know it need now to download the page towards the TCP IP. So this is what will be the first thing here. So once the TCP IP receive the packets coming from the application layer, it will start adding headers and forward this data to IP layer. Actually, the header part, you need to know, it's a really very, very important thing. You need to understand it whenever you study about any of these kind of topics, because the header will make it very clear to you about any of the functionality. For example, if you look into the bottom left here, we have the TCP header format. You can see the data coming from the application layer. There is a header added, being added for this data, and this header will be helping the TCP layer, for example, for the retransmission, to track the packets to know whether it's coming out of order or it's coming in order or it's being packet loss and so on, and also to try to identify which IP layer is going to be used here. So, for example, here there is something called source port and destination port within the header. This is just source port and destination port, identifying the client and server or the entities where we are going, the destination where we would like to send this kind of packets and so on. We'll explain this part in the TCP part as well. But the most important here, that's adding something called sequence number. And sequence number here, you will see it also in the BDCP and the RLC, because sequence number is mainly used to try to track the packets. Each packet will have a sequence number. So, for example, this sequence number can help to, for example, I assign for the first packet as sequence number 1, second packet sequence number 2, third packet sequence number 4, and so on. So this like will be helping to track these kind of packets to know whether it's being lost or coming out of delivery. So this will be helping the application layer. We have multiple other things like checksum for example, to check whether there is any errors in the packets or not. And when sites, we'll try to cover this as a high level perspective in the TCP point of view. But in summary, the TCP will be adding a header to the data, which will be helping the TCP itself to do this kind of reliable data transfer. Because as you know, also TCP is supporting retransmission, ARQ, which is for the used for the retransmission. So once the data is being sent, now it will be forwarded to the IP layer. Then the IP layer again, it will add its own packet, a header to the data as well, which is coming for the TCP. And this again, just quickly, this header will identify whether this is IP version 6, IP version 4, and whether there is any fragmentation or not. But this is one of the things the TCP will try all the time not to ensure there is no IP fragmentation. So this also can be information in case if there is a fragmentation, this will be highlighted within the header. And also the protocol being used, it will be addressed within the header. For example, here it knows it's coming from the TCP protocol, which is using protocol number 6. And also it will have some kind of header checksum, which is validate the data integrity. And the most important, it will be including the, as highlighted, the IP version and source and destination IP addresses to know where this data is going to be sent for which destination, just the exact address and so on. So this is point number 5. Once it's received from the IP layer to the IP network, then the IP network will packet the IP packet, which is coming from the IP layer, will be routed through the IP network layer towards the UBF. And as you know, UBF or user plane function in the 5G is the first or the core entry point for the 5G core, is the 5G core entry point. So this is what's responsible for, as you can see here. Once IP packet being received, which is the TCP IP packets coming from the application towards user plane function, it will be mapping, the user plane will be mapping that into a specific quality of service. It knows that whether this data need a specific quality of service and within which BDU session. Then it will be forwarding this data through the NGO interface to the SDAP layer. And the SDAP layer, as you know, this one which is mainly responsible for mapping this kind of quality of service to a specific data radio bearer. As you know, the RAN protocol in general is dealing with data radio bearer, DRP, right? So this is just very simple, as you see in these two pictures. If the data is coming here, for example, this is saying this is the tunnel 1, this is the tunnel 2, we have BDU session 1, and this is quality of service. For example, we have 3 packets, each one have a different quality of service, E, B, and C. So the SDAP layer will know, okay, will tell them, guys, this quality of service A needs to be mapped to DRB1, B need to be DRB2, and C need to be for DRB3, and so on, as you can see here, and also on the bottom right here. So again, this is the main responsibility of the SDAP layer to map the quality of service to be mapped into a specific data radio bearer. And then moving forward, once the data moves from the SDAP layer to the BDC layer in the downlink direction, you can see that BDC again will be adding a header on top of this data, which is coming from the upper layers. And the most important for now to know about the information that the header is related to sequence number, okay? The sequence number, because the sequence number used for example, as mentioned here in this point number 8, reordering at the receiver side. Once the data being received at the receiver side, which is the UE here, this will know that this packet is coming, for example, if he received packet 1, 2, and he was expecting 3, then he received 4, he will know that this packet is out of order, so he will be waiting for a specific timer to make a reordering for the packet in order to transfer to the upper layer. So the sequence number is very important for the retransmission to track the packets and also for the reordering at the receiver side. So this is the most important one for now. We'll also covering other of the headers, but the headers of DCP is not that much. Today, actually, we'll be covering the RLC, which is actually one of very, very, I will not say complicated, but have a lot of things to be explained. This will be explained today. So the RLC layer, again, will be adding a header on top of the BDCP, which is coming here. So the more you go down, the higher the headers, the more the headers you are getting. So you get the RLC header. Again, it will be adding a sequence number related to from the RLC perspective. And this sequence number, I will be explaining in details what to do exactly. Again, it needs for reassembly at the RLC receiver, and also multiple other things I will be explaining in details here. But it will be adding a header and forwarding the data towards the MAC layer. And as you can see here, this is just a quick summary here. This is as you can see, this is AMC acknowledgement mode RLC layer. We're using acknowledgement mode here because we're using HTTP. So this like will be using, as you know, the RLC having three transmission modes. I'll explain those in the high level also in the RLC part, which is the transport, TM, acknowledge mode, and acknowledge mode. So this will be using acknowledge mode, which is having this capability of automatic repeat request, which is ARQ. So here RLC layer, there can be a segmentation, resegmentation, retransmission, and also reassembly at the receiver. This will be explained in details. So the RLC would be forwarding the data towards the MAC layer. Then MAC layer's main job is doing, one of the main job is doing the multiplexing for the data was coming from the RLC into one transport block or two transport block, depend on the requirements. Then it will be forwarding that part through the transporter channel. For example, here transporter channel will be downlink shared channel. Then it will go through the air interface and it will be moving back up to the UE. And here you will have a reverse. For example, once we go to the MAC layer, you will have a demultiplexing for the data. Here, the RLC, if the data was being segmented, RLC will have reassembly. This all will be explained in details. And in the BDCV, as we highlighted, it was adding a sequence number. Here it will just doing the reordering if needed, if the data is coming out of order, and also other jobs. I will be explaining all of them in the BDCP part. Then it will be going back from SDAP until it reaches to the application layer. One of the most important things I would like to highlight before moving to the next slide, that there is multiple retransmission mechanisms within all these kind of things. For example, the TCP can do a retransmission. The BDCP can do a retransmission. RLC can do a retransmission. And MAC also can do a retransmission. But the more robust and faster one is HARQ, which is a MAC layer, because this is using hybrid automatic repeat request. While the TCP is using RQ, automatic repeat request, also RLC was using automatic repeat request. But all of these is being used to guarantee that a less packet loss and the data reliability is very high to ensure this kind of service HTTP or fast file transfer is being happened in a proper way. Also, there is a retransmission of the BDCP layer. I was explaining that part, but it's mainly within during the inter-GNLP handover. I'll explain how this being happening, but in the BDCP session. And that's it for this part. Now let's move to the next part, which is related to a high-level introduction about all the parameters and timers within the RAN protocols. I'll give you a quickly high introduction before going to the visualization part, which will make it more easy for you to understand. So moving forward here, as you can see in this table and the figure on the right, this is, we can say, all the parameters and most or all the parameters, RAN protocol parameters, from the BDCP till the MAC layer and the RLC layer, which is related to the RAN protocols, parameters and timers, which is being considered during, you will find it in any of the networks for sure. This is, you might require to be very careful whenever you are going to tune on any of them. So again, we already explained how that it is being transferred. So here I'm assuming you have a transmitter and receiver. So this is applicable even for download or upload. So download, it will be GNLP towards the UE. If upload, it will be UE towards the GNLP. And at the end, any of them will be acting as a transmitter and any one of them will be acting as a receiver. So the first timer I'll get start with, this is at the transmitter. You can see we have timers at transmitter and timers at the receiver, timers and parameters. So the first timer called discard timer. This is at the BDCP. Once the data received from the upper layers towards the BDCP layer of the GNLP, for example, or the UE, what we'll see, there is a timer will be starting at the BDCP. This timer is just like a buffer time. For example, if the packets retained or stayed in this packet for longer than the particular the duration of this timer, the GNLP itself will be discarding. The transmitter or the UE will be discarding this packet, so it will be counted as a packet loss. So this is one of the things. So again, increasing or decreasing this timer can increase the delay or reduce the delay, but in the opposite way around, it can also have a better packet loss or less packet loss. This will be explained when you go in details for the next slides as well, whenever you go to the BDCP and CP part, to see what kind of relation and consideration you need to check whenever you do this kind of tuning. Then you have the RLC. But before doing all of that, I would like to explain a very small part here, which is related to the SDU and BDU. Just to because sometimes you get confused or you forget about the name. The input of the layer, whenever it's coming from the upper layer, it's coming as SDU. When you enter the data, it's coming as SDU. SDU means service data unit. This is pure data, without any headers added yet by the BDCB. Okay, so this is the meaning of the SDU. This is the pure data coming from the upper layer to BDCB before adding the headers. Once the headers of the BDCB or RLC or MAC or whatever is being added, it will be called MAC. It will be called BDCB. For example, here this will be once the entry point would call BDCB SDU, and output here from the BDCB once header is being added to the data, it's called protocol data unit, which is called BDU. Okay, this will be the output, but again at the RLC layer, the BDCB BDU will equal to the RLC SDU. So once it reaches to the RLC, it will be called now as RLC SDU. Okay. So just to clear this information, because we'll be highlighting SDU, BDU all over the session when we are moving. So now moving to the RLC layer have multiple timers and things. This will be explained in details, maximum retransmission, T-ball, polling feature, ball BDU, ball byte, and many other things we'll be discussing. Here the MAC will be responsible for the HARC in general, especially for the HARC transmission whenever there is a transmission. So the main parameter here will be related to the maximum number of allowed HARC retransmission. Also here, RLC, there is a maximum number of allowed retransmission. And the receiver side, this is like you have multiple parameters as well. At the RLC itself, you have something called key status per head. I will explain this part with examples in next slides. And TRI assembly, also will be explaining this part in next slide, but simply TRI assembly will be started whenever there is a segmentation. If the RLC thought that the SDU will not be fitting a transport block and the transport block size is less, as being communicated to the MAC to the RLC, it will be doing a segmentation for the packet into a small packets or small SDUs and BDUs, RLC BDUs, that will start fade into a different transport block. So if the packet is being, let's assume RLC SDU is being segmented into three, so whenever it reaches, these three packets reach the RLC, when the first packet is being reached, the RLC need to start a timer within this timer, it needs to wait for the reassembling this data into one bucket again before transferring it to the BDCB layer. I'll explain the function. And again, the BDCB now will be doing the reordering of the buckets. In case of the buckets, if you remember, we mentioned that at the header of the BDCB, there is a sequence number being added. So assume that the sequence, you have a three buckets, 1, 2, 3. Assume that the BDCB received 1 and 3, okay, and it didn't receive 2 yet. So it will start this tier ordering. Once it receives 1, 3, it will start the tier ordering time, waiting for this timer before it forward the data to the TCP layer. Just it want to ensure that there is a correct ordering of data being forwarded to the TCP layer. And the main reason for that, can reduce kind of retransmission or selective acknowledgement from the TCP. We'll be explaining that part later on, but in case theory ordering ensures the data is being transferred to the upper layer in a sequence, in a correct sequence, 1, 2, 3, 4, 5, 6, and so on. This is the main idea. And also there is parameters called out of order delivery. All that will be explained, but today we'll be focusing on the RLC because as you can see, the RLC have most of the parameters we are explaining here. So now let's move next to see in details, and it will be very interesting about all the functionality with a very good visualization for each of the functionality for RLC functionality and the timers being used and parameters used by the RLC, and also some how the RLC interact. So let's move forward, see what we have. So this is, I just tried to give a quick introduction for what's going to be introduced next in today's video about the RLC. As you can see, many things here. First thing here, I would like to give you a quick introduction about the RLC transmission mode. You might be already aware about it, which is I highlighted at the very beginning. You have three transmission modes, which is acknowledgement mode, unacknowledged mode, and the transport or the TM mode. I'll explain what is the function with each of them, and I will show an example from the Wireshark as well to show when this being happened, how it's being handled, and so on, and why it's being used for each of those modes. Then we'll go through RLC layer functions. I will give a quick high-level introduction about the functions. Then for this function, we'll take it one by one. And the second one, related, for example, segmentation, one of the function, the resegmentation is one of the function, retransmission, this also will be considered in a deep dive. But I advise, before I go for this kind of function deep dive, I will be explaining the RLC BDU headers. you need to understand the headers very well, because if you understand the headers, and it's easy one, if you understand it very well, you will understand whatever is being happening at the RLC in terms of freeze transmission, segmentation, resegmentation, and in case if you have any Wireshark logs, you can do the analysis for these Wireshark logs easily if you understand about the video header. So don't skip the header part, because without the headers part, you will not really easily understand the remaining parts. You can understand it, but not that easy. So the header part is very important. Okay. So this is what we begin to cover. Then we'll show you quickly how I can check all the related parameters, which I highlighted in the previous slide, through a speech fidelity through the draft test logs. Then the most important also, I will show you what kind of consideration and time relation between the RLC and the HARC or the MAC layer, what kind of consideration. Then I'll be ending by the RLC layer, the main functionality differences between 4G and 5G, and what kind of improvement being added to the 5G when you compare to the 4G. And this is was a very good improvement being added, and this also was one of the reasons of the latency improvement. The last part, this will be already covering whenever you go here. It's related to, as you can see in 3GP, there's something called constants. This is related to the window size, timers, configurable parameters. All this already covered. The state variables, I didn't cover indirectly here, but I will just be adding a table highlighting what it do, and also have a link. I will be adding a link which is showing a very clear visualization for that, explaining the state variables if you are interested to know about these state variables, but will not really need it for now. So now let's move forward, see what you have to cover all these parts in today's session. As you can see, it's very long. Before jumping into the details of the functions of the RLC layer and the visualization part, I would like just to recap a quick and important information about the RLC in general. As you can see in general, RLC in general having a three something called transmission modes. Okay, as you can see in this figure, you have transmission mode called transparent mode, and this is actually the main function of this one. It's passes the data without adding any RLC headers. Why? Why there is no RLC headers? Because this actually RLC transparent mode is completely, RLC is completely transparent and essentially bypassed. It will be bypassed directly. There is no retransmission required, there is no duplicate detection, and no segmentation reassembly take place. And this is mainly used, as you can see, as a service point of view, using something called signal review bearer 0. And signal review bearer 0 is mainly used for the control broadcasts, such as broadcast channels, and also the paging, and where this information need to be reached to multiple users. Just I will tell you like examples. Also, this will be showing next about the same from the Wireshark. But as you can see, the SRB0, signal review 0 here. For example, this is for 4G, but it will be 5G as well, called transparent. This is during, for example, the RRC connection phase. Whenever the user is going to send RRC connection request and receive the setup, this will be done using the transparent mode. There will be no acknowledgement. Afterwards, for example, SRP1, which is starting from the RSC configuration, release, and command, security, and UE capability information. This will be using the SRP1. And the SRP1 actually required an acknowledgement from the user side. You required to use RLCM mode, which I will discuss shortly about that one. But this is the first information about transparent mode. If you look into the figure in the bottom left here, there is a control plane, as you highlighted before, and user plane. The control plane will you be using the SRB0 as highlighted through using transparent mode, and this is the transparent mode here. And in transparent mode, it's acting as unidirectional. You should have one entity for the transmitting and one entity for the receiving. We don't have the same entity doing uplink and downlink. The same entity will be mainly used during the AM mode, as we'll be highlighting shortly as well. So this is just one of the points to explain about this kind of figure. If you see it anywhere, that the TM mode is unidirectional for downlink and uplink transmission. Then moving forward for the unacknowledged mode. Okay, this is called unacknowledged. This is type here. This is unacknowledged mode. Okay, this is actually mainly required for the service which require the low latency delivery, which doesn't require any RLC transmission. It can have HARC transmission in the MAC layer, but there is no RLC transmission because usually the RLC transmission actually is very slow, so it doesn't require any RLC transmission. And this is, as you can see, it's mainly used for the data radio bearers only. It's not used for any of the signals, and it's used for idle, for real-time applications such as voice over an R, as we highlighted here. And actually, this is again, mode is used when error-free delivery is not required. We don't require error-free, for example, voice over NAR, or even for the video or for the VoLTE. So this one, but it's very sensitive for the latency and response and so on. Last part, which was being to cover in details in today, this will very important, where all these kind of timers in the right here is mainly at the acknowledge mode. Most of it, few of it, it's at the unacknowledged mode as well, but most of it is at the acknowledged mode. And this is ensures there is error-free delivery with retransmission and flow control. There is a flow control. It require also that error-free delivery, especially as we highlighted for HTTP, FTP. This require error-free delivery services. So this is used, for example, for critical, even for the specific services for the signaling, as we highlighted for RC configuration, SRB1 and also SRB2 can use acknowledge mode, as you can see here, or it can use for data reducer in the user plane, as you can see as well for the BC. And this is actually bi-directional, not uni. This is here for that part, as you can see, the acknowledge mode is bi-directional. As you can see, it's working as transmitter and receiver in the same time, while for the UM mode is working as a U direction. Now let's move to the next part about the functionality of the RLC. Then we'll take it one by one to break it down with a visualization examples. Just quickly here, this already explained, but it was quickly here I tried to summarize a function of the RLC, which is related to the specific transmission mode. As highlighted, for example, for the AM mode, you can see it's having error correction through automatic repeat request. This is the retransmission part. This is mainly supported by the AM mode. It doesn't support it by any other order, any other mode, as we highlighted. Segmentation and reassembly, can be by the acknowledge mode or the AM mode. This means that the timers related to reassembly can be configured for both of them, not only for AM, can also consider for UM. And by the way, these timers, as you might now understand, it's defined per QCI. For example, QCI 1 will have different timers compared to QCI 9 or 6 or 7 or 5 PQI, in other words. Same for 5 PQI 5 or 1 or 5 PQI 9. So this timer is being defined for different PQIs or QCIs. This segmentation of the RLC, there is a segmentation. There is a resegmentation. This is mainly happening during the retransmission phase. When you have a retransmission, the RLC can decide to do additional resegmentation for the packets. I will explain this one in detail in the next one, but it's mainly all happening during the retransmission. That's why it's only the AM mode, because AM mode is the only acknowledge mode is the only one which is supporting the retransmission. Duplicate detection at the M and UM. If there is any duplicate packets being received RLC, the RLC can handle that part through discarding these kind of packets. Through discarding, as you can see here. So it can detect through the sequence number whether you have a duplication or not, and also it can be discarded by the RLC in two cases through the flow control. This is also be explained, especially during the BDCP. If they have a flow control based on kind of timers buffer, you would like to reduce the buffer or discard some of the packets, so the RLC still can do a discarding for these packets. Now let's jump into the next slide, which will be very, very important, about how this kind of functional working in the details aligning with the timers. But just in the next slide, I will just showing you a snapshot for this function in the details. Just if you would like to take a snapshot out of it, explaining the details in one table. Here you can I already explained all that. Now you can just take whatever you want as a snapshot in case you need to have more explanation about each of these functional to just highlight it. Now let's move forward to the next one, which will be more details about each of these function with visualization example. As I highlighted, before going to the visualization example, you need first to understand about the headers, which can be used for the acknowledged mode data or RLC, right? So as you can see, this one on the left or the right, it's kind of I just show it based on whenever you don't have a segmentation, whenever you have a complete RLC BDU without segmentation, this will be the headers. You have something called DC. This DC just like explaining whether this data which is being sent from the GNet B from the RLC layer and from the transmitter to the receiver, for example, is being controlled or used for control or data. The reason is for control data all the time is prioritizing over the data. So if you have a control BDU and you have also transferred data BDU at the same time, the receiver will be handling the control and also the transmitter in more priority compared to the data. So this will be explained as well. And you have something called polling bit. Polling bit, as you can see here, 0, 1. This is whenever the transmitter is requesting the receiver to send a feedback about the data, whether this data is being received correctly or not. For example, send ACK and NAC. So it will be setting this flag into 1 if it's requesting the receiver to send a response, telling them, please, I need a response now about this segments or sequence number to tell me whether this is being received correctly or not. And the sequence number, as I highlighted, sequence number will be added for each of the RLC BDU packets. Each RLC BDU will have a sequence number to allow the receiver to track this kind of sequence. So he can reply, for example, acknowledgement for this sequence number 1 or 2 or 3, or NACS, for example, telling him that I have non-acknowledgement for sequence 3. I did receive sequence number 3. So identifying which packet that was not being received. And this is here. And you have something called SI, segmentation information. This is just whenever you do an analysis. For example, if coming as 00, as you can see in the Wireshark down here, 00 means this is a complete RLC. It's not segmented here. And if it's segmented, it will take this kind of format, segment information, telling him, for example, first segment, this is the first segment. So once you receive the first one with 01 here, as you can see from the RLC here, receive this one as 01. This means this is the first segment. So the receiver will understand you need to start his reassembly timer to start waiting for the other segments to do the reassembling. Then you have, if the second packet being the last packet being received, it will be setting at 1 or 0, and any packet in between between the first and last will be set as 1 1. So this is telling him this is not the first, not the last packet. And here is just more details about whenever you go to the sequence segmented one. In the segmented packets, this was for complete RLC. We have additional headers. For example, we have, as you can see, this is all for cover. This one cover is only the sequence of offset was not being covered here. The sequence offset is just telling him, for example, the start and end point of the packets. For example, telling him that this packet, for example, BDU sequence number BDU1, sequence number 0, and all the segmented one will using the same sequence number for sure, because at the end it's same packet but it's being segmented. But it will tell him, for example, the SO, which is sequence offset 0, this telling him this my packet starting from 0, for example, to 2000 bytes. Then he will tell him my second starting from 2000, or from 0 to 1999. Then second one will tell him, for example, my packet starting from 2000. Then this one will tell 3099. Then he'll tell this one will tell him starting from 4000. So just telling him the bytes which is being captured by each of those packets. So try to understand this very well, because this will make it easy for next slides. Now let's move to the very interesting part for the RLC. So in this example, I'm just doing a quick example how the data will flow from the RLC layer in case if you don't have any RLC, that packet was not being segmented. It means the complete packet would be transferred directly to the MAC. So I assumed here you have at least 3 RLCs due coming from the BDCB layer. As I highlighted you, the output of the BDCB called BDCB BDU, but it will be the input of the RLC called RLC due. So I'm like assuming here we have 3 different packets. First one assigned with sequence number 0, second one with sequence number 1, then you have third one with sequence number 2. And this is RLC acknowledged mode is due. This is A for acknowledged mode, AM for acknowledged mode data is due, and this being transferred. Now the RLC need to add the headers, right, as we highlighted before. So it will add the headers, including the RLC sequence number. For example, here is saying this sequence number 0, and SI, as highlighted before, is telling him that the segment information, it's complete is due. So it means that it will have 0 0. If it's segmented, it will have 0 1 or 1 1 or 1 0, as we highlighted in the previous one. So here is telling him this is the first one, sequence 0 1 2. Then once the data moves directly from the RLC to MAC to the MAC layer, the MAC layer will add its own headers as well, as you can see here. So it will be RLC AMD plus the header. It will be output as RLC BDU. It will be going down for the MAC as MAC is due. It will add the header. Then it will be forwarding that. It will do the multiplexing. The MAC layer will do that. Will to multiplex all these layers, and it will assign it to 1 transport block or 2 transport block, depending on the size, to be transferred through the transporter channel, which is called, for example, downlink shadow channel to the physical layer. So here how it looks like from the traces. From the traces, for example, assuming this is downlink, so Juno B will be forwarding the first packet and telling him this C1. 1 means this data, not control. Sequence number is 0. Pulpit, as I told you, is not requesting any acknowledgement from the UE yet or from the receiver yet. Just telling him, I don't need any request, just keep receiving without sending any acknowledgement. So This will be considered discussing details about the polling also in next slide as well. So let's see video size. It's telling this is the video size is 100 bytes. I have this one as 100 bytes. Then it's sending the second one, sequence number 1. Then start the sequence number 3, as you can see here. And this was, as you can see here, the ball bit here was set to 1. Okay, the ball bit was set 1. And once the ball bit set 1, this means that the transmitter is requesting the receiver to send the feedback. Here it's relating to send something called RLC status video or report, telling them what is your status. Did you receive this packets or not? Please feedback to me. Here the TPOL will transmit. Timer will be starting. I'll be explaining this in details, but just start whenever this ball bit is set to 1. It will be started from the GNB side because this is at the transmitter or transmitter. Whenever this is downlink data, if it's uplink data, it will also set at the U side. So this is how the feedback looks like. This is C here, DC equals 0. This telling him there's a control, okay? And here is telling him the CBT equals 0. This means CBT equals 0. This means because there is another header for the video, but I will not explain this one in details. But just simply CBT equals 0 means this is RLC status report. And here it's telling them, okay, acknowledgement sequence number equal 3. So here you received 0, 1, or 2. So here is confirming. I'm waiting for now for the next acknowledgement sequence number, number 3, because I acknowledge that I received 0, 1, and 2. I will be showing an example whenever there is non-acknowledgement, how it looks like. And again, from the white Wireshark perspective, again, this will be showing as here. For example, as you can see down here, this is DC equal 1. There was data. Pulpit was 1. Pulpit this one, requesting him to send RLC video. Then sequence 00 and sequence number 98. You can see the receiver replied was DC equals 0, which is this one. Then you have CBT equals 0, this one. Then acknowledge sequence number. Here was 98. Then again, I'm waiting for next one because I already acknowledged that I already received 98. But one thing here, you might ask yourself, when the segmentation will happen or without segmentation? Usually, actually, the MAC will inform the RLC about the transport block size through the MAC communicates the transport size, as mentioned here, to the RLC through the uplink routes, if it's uplink data or downlink allocations. And the MAC informing the RLC about the transport size or the current transmission opportunity. So the RLC at that time will decide whether it needs to do a segmentation or the packets can directly fit into the transport block, which is being allocated by or the information being allocated by the MAC there. Now let's move to the non-segmentation part, see what we have. But before we move into segmentation part, this is a complete example for the all the SRB0, 1, and DRB. As you can see, we highlighted before that spot as well. For example, SRB0, as you can see, this is happening again during the connection request and connection setup. And this is mainly using the transparent mode, as we highlighted before here for that SRB0. This will use an acknowledgement. There is no any acknowledgement. There is no any retransmission, nothing at all. SRB0, once you move to the SRB0, as you can see here, this is using sequence number 1, MAC, but this is require an acknowledgement again, because this we're using the acknowledgement mode, right, for SRB1. When you move to the security or your capability or RSA configuration. So that's why each time it was being sent, it was being acknowledgement directly here for each of those packets being acknowledged directly. Then we move to the DRB part, which we just explained it here. For example, here is telling them this is RLC, acknowledgement mode, headers, as we just explained. Now let's move to the segmentation. So this is about the segmentation part. Simply, it will be very similar to the other, but it will have additional headers as I highlighted before. So here, for example, the one in the left here, I assume this one as a complete, doesn't require any segmentation, which is having segmentation information as 001, 00, as highlighted down here. This means complete is 0. But assume now that this one is a big one having a big size and it's not fitting into a one MAC SDU, or it's not fitting in one transport block and need to combine two different transport blocks. The size was big, so it needs to be segmented from the RLC layer. So what will happen at that time? As you can see, the RLC will decide the segmentation. So it will do a segmentation into 3, for example, here for this 250 bytes. So the first one here is having sequence number equal 1. All of them will have the same sequence number because at the end, this is one packet, but it's being segmented. So all the segmentation will have the same sequence number 1, 1, and 1. Okay. Then here the segment information, as I highlighted to you before, 1 means 01 means this is the first segmented SDU, and anything in between the first and last will have 1, 1. telling him this is the segment information 1 1. This means it's not the last, it's not the first, it's something in between. But again, you have another information called segmentation offset. This is highlighted in an example, highlighting what kind of packets is going to be transferred, starting from which point. For example, here the packet size was from 0 to 49. So he's telling him this will be from 50 to 99 bytes, because the next one will be coming with, as you can see here, with a segment information, segment offset. This should be 100. By the way, this is a type as well. So this tell him from 100 to 100 to 49. And segment information is 10, means this is the last 10. As you can see, this is the last segment of the SDU. So now it's being received. Now what's being transferred to the MAC? The MAC will decide whether to, it will do the multiplexing again, and then it will start assigning to a transport block. It might assign to the same transport block, to different transport block, but it will ensure there is a less padding as much as it can. So this is expected not to have any padding. So this will be the job of the MAC to do the multiplexing. Same as the previous example. DCI, this means data 1, sequence 0, which is the non-segmented. This size 100. Then the second one coming here with 3 segments, as you can see, sequence number 1, 0, 1, 50 byte, and so on. Then at the last one, which is last segment here, there is a ball bit equal 1 being added, and the T-ball retransmit whenever the ball bit is being set. Then here there was no problem, so directly the UE or the receiver side acknowledgement that sequence number 2 is waiting. So now he receives sequence 0 and 1 acknowledgement. So he's waiting now for the next one, which is sequence number 2. Now let's move to the resegmentation example. Here this is segmentation. There is a resegmentation as well. And I highlighted before, resegmentation is only happening at the M mode, because this is usually happen when there is a retransmission. And this is actually one of the things why also the RLSE can work as a complement for the HARC that can give even better performance sometimes whenever to do resegmentation. I will explain that part, but let's move for this one before going to the very detailed one about the retransmission. Okay, this part, it's about the resegmentation I highlighted. Again, here, as you can see, I assumed in the beginning, in the original transmission, as you can see here in this figure, there was RLSE was being segmented into 2 buckets. So the example here highlighting there is two segments being created from the original segment. So this was the original transmission, which having a segmentation. Assume now there was a failure and the receiver didn't acknowledge that one. Now the RLSE layer need to do the retransmission, and this was not being even successfully decoded by the HARC as well. So it required RLSE retransmission. So sometimes the RLSE will decide to do additional segmentation to the originally segmented packets. So as you can see in this example, this segment 1 and 2 will be again resegmented into additional 2 buckets here. And the main idea of the resegmentation, whenever you reduce the number of the layer, for example, because whenever it's being resegmented, so when it's resegmented, this means it will have a smaller segments, as you can see down here, and smaller signals are less likely to encounter errors, and this is increasing the retransmission success from the receiver point of view. So this can be one of the benefits for the resegmentation, which is happening in the acknowledgement mode. So as you can see here, and just one last example here, as quoted from the 5GNR and BoltzFock, as you can see here down here. This just demonstrates that resegmentation can combine data from multiple original segments to produce a new set of segments. What it means by this, if you look into this, this was his one original transmission, as you highlighted here. It was segmented into 3 segments. Then it takes one of the segment 2 and part of the segment 3, and this one producing a new set of segments. As you can see, it's combining both of them into a new one. So this is the meaning of this statement. So now let's move to the retransmission part, which will have also more details. As we highlighted in the very beginning, automatic repeat request or retransmission in general is one of the main functionalities of the RLSE in acknowledgement mode, as highlighted here. And we highlighted also that transparent mode doesn't require any transmission, because actually there is no uplink yet established, and unacknowledged mode, there is error-free delivery is not required, right? So here we're going to discuss 3 topics actually. The first one related to something called window advancement mechanism. You need to understand how the transmitter and receiver, there's something called window size, which is deciding the sequence numbers and throughput and many other stuff. I will be explaining that part in details. I will be explaining that with a high-level example, visualization examples, to see what is the relation of the sequence number and what kind of transmission window and reception window we have, and how these kind of windows being working. Then we'll deep dive into the polling features related to the receiver transmission, including the polling events. Whenever polling means whenever the transmitter needs a status report from the receiver. In general, when the status report will be sent from the receiver based on which timers, and also timers and parameters will be discussed in detail. Then the last part, which is very interesting as well, we'll be discussing about the relationship between the ARC and HARC, in other words, between the RLC and McLear parameter relation and consideration whenever you are tuning your network parameters. So now let's move to these three parts, which we can cover in details now. This part is important to know it, yet it's not really, we are not really looking into it if you are speaking about the RAN domain, but in general, you need to really understand it just from theoretical at least, and also sometimes maybe you need from practical point of view. You can see here in this figure, in this figure, as you can see in the right side here, we have three examples. Example number 1, 2, and 3. And these examples have some blocks inside. These blocks, just as you can see from the color code here, the red one is saying that this RLC is being transmitted. The green one saying that this one being acknowledged, and this one means it's not transmitted yet, and this means it's free. There is nothing else yet happening here, and this one means successfully received by the receiver, and this means there is ambiguous RLCs due. I will explain that part here. But the first part you need to know, the window size in general, this is like explaining how much data can be transferred from the transmitter to receiver. For example, let's say the window size deciding the maximum throughput within the window size. For example, the window size here, quick example, I will explain how it's being calculated. The window size here, it's equal to, for example, 2,048 bytes. So this is the maximum bits can be transmitted, for example, within this window size. So the higher the window size, the higher the speed you can get. Okay. So one of the advantage from the 5G compared to 4G that you have now higher window size, and how window size is being calculated is calculated based on sequence number. You have a sequence number of bits. For example, currently in 5G you have two configuration, which is 12 or 18 bit. You'll find it's all the time used as 18 bit. 18 bit, means it's equal to this number because it's 12 power 18. So it will equal to this number. Then the window size in general equal half of this number. So you need to divide this number by 2. So this will be your window size. So this is the relation. First of all, the sequence number decide what is the window size. Okay, window size will be decided based on the sequence number. So the higher the sequence number, yes, it's higher overhead, but it's very needed for the higher throughput. Okay, and also the higher sequence number can reduce something called ambiguous RLC or the window stalling. I will explain this one part now. So sequence number in general, as you highlighted, it's like used for detecting duplicate or missing data, maintaining the order delivery, and also enabling precise retransmission in general. Okay. So now let's explain how this kind of window is being working. Assume now you have this figure, this one. This is your acknowledgement window size. This is your window size. Okay. And this is one example. You can see this is from the transmitter point of view. The transmitter, for example, the window size will be initially, for example, starting here. Then it will be starting shifting whenever you have acknowledgement. So the transmitter will be shifting his window size only to the right side, for example, once the data is being transmitted, it's being acknowledged. For example, this green one, acknowledgement from RLC view. This means he received acknowledgement from the receiver that those 5 packets being received. So this means he can advance now his window size. So initially window size will be starting here. So it moved to the right once being acknowledgement as sequence number 5. So we'll be starting now from sequence number 6. So 6, 7, 8, 9, and 10, 11, it's being transmitted, but it's not yet being acknowledgement, so he cannot advance. So he cannot yet advance, but he still have some data in the buffer not being transmitted, so still he have a probability even to send more data, so still there is no problem here. The second example here, it's similar to this one, but you can see sequence number 3 here in this time, it was not being yet acknowledged by the receiver, so that's why he didn't move his window from to the right. For example, here is starting only from the 3, which is the transmitted one, even though sequence number 4 and 5 is being acknowledgement, but he can move it to 6, for example, because 3 is not yet acknowledgement. So we have to wait until the retransmission is being complete and until he received sequence number 3 from the receiver as being acknowledgement and received by the receiver. So in this case, still we have 3 packets or 3 free slots can be used to transmit a new RLC. So still here we don't have a problem. But now assume those three is being filled, okay? And sequence number three is not yet being received from the receiver, not being acknowledgement. So this one will cause something called Windows stalls. This means you will have your data will stop here. You cannot transfer a new data. So this will can, for example, can cause a lot of problems. As you understand now, we cannot transfer any new data, so your window will stalls. And this is actually one of the important things you do. Like that's why you need to have a fast retransmission, try to recover your data as much as possible. Also, there is another scenario I would like to highlight it now from the receiver point transmit and window size from transmit and receiver. Sometimes the receiver can advance its window size to be like more faster compared to the transmitter. Why? Let's see this example. This example in the top left here showing that the transmitter side transmitted from packet 0 till 11, but packet 0, 1, and 2 being and 4 and 5 being acknowledged, but 3 not yet. So as you understand now from the previous examples, now the window size will stop here, right? It cannot be transferred until this one being acknowledgement, and also the others. So it will stop here. If this one acknowledgement, it will be moving to starting from 6 here. And the other side, the receive window from the receiver side point of view, he will advance his window once he successfully received the RSC. He received the RSC, sent the feedback, he don't care. He will just directly advance. So assume now he received from 0 to 11 and he even acknowledged 3, but it's not yet somehow not the feedback not being received by the transmitter. So in this case, he will advance his window from example here to here. Okay. Now this example, assuming that you have a very low window size, you are using, for example, using a very window size, for example, let's say 12, and the data was being on the receiver here, as you can see, from 0 till 19. This was the end of the window size, so it need to again start a new one with from scratch, from 0 to 19 again. This is just giving a very small window size for illustration. So now this means that this is now 0, 1, 2, 3, 4. This is repeating the data, but it's a new actually data. So what will happen in this case? Because the window size is low, this might cause something called data stalling or ambiguous RSC view. What it means by that, you can see here. Because the receiver advanced his window more faster compared to the transmitter, because it's only based on the received data once you received. So now it will be starting his window from 12, but now you can see part of the data at 0, 1, 2, 3. At this particular time, the transmitter decided to retransmit as U number 3. But the problem here, because this one is being advanced here, and because of the window size issue, window size is low, the receiver will think this is a new packet. It's not a retransmitted packet, which was originally here. So in case if you have a higher window size, now you can see that if it's high window size, let's say this will be 20, 21, 22, 23, 24. So this, in case if this one retransmitted, the receiver will understand that this one is retransmitted, it's not a new one. So this will clean this kind of ambiguous RSC view. This was the main idea of increasing also the sequence number, which can improve this kind of probability, especially in the 5G, because sequence number in 5G, which is meaning translating into window size, is much bigger compared to the 5G, as we'll be showing in the very end of the slide. And now let's move forward to the next part. Now, let me explain to you about the polling feature in general. This part of the retransmission in general as well, how the retransmission can happen. So we have multiple parameters actually. As you can see here, we have poll BDU, we have poll byte, we have T-poll retransmit, we have the maximum also retransmit threshold. And from the for rate of the polling as well, from the receiver side, we have something called T status per head. Okay, so you can, what's the explanation of those? I will just need to explain with an actual example. You have poll byte or poll BDU or poll byte, which is these two parameters at the transmitter. This is just explaining when the transmitter will decide to send to the requesting the receiver to send a status report, to requesting the receiver to send a feedback about the transmitted packets, which are being accepted or acknowledgement or not. Okay, so this example, assuming that poll BDU is equal number 3. Poll BDU means the total number of BDU, RSC BDU means packets can be transmitted within a poll. So 3. So this means after 3, as per the explanation, once this number is being reached, at the packet number 3, 1, 2, 3, the transmitter will be requesting the receiver to send the feedback. Okay, and the T-poll retransmit, this will be started once the poll bit is being set. I will explain this one now, and this one will be explained in a different example related to poll byte. Okay, T status per head Once the receiver send the feedback, he will start the timer saying that I cannot send any additional status report until this time expires. For example, assume that the transmitter now suggested that I need the status report now. I need from you to know what is the status of the package which I have sent it now. So the receiver will be in reply telling him this is the back. Then after few milliseconds, 2 milliseconds, the sender again send another one. So in this case, the receiver will not send any feedback until this timer expires. And this is kind of used to secure that there is not excessive number of reporting being sent from the receiver to the transmitter. Now let's see an example. This one, assuming the poll BDU, the number of polls or BDUs within a poll is 3. So assuming now the first packet will be transmitted from this sequence number 0, poll bit still 0, and this is the second one, sequence number 1. Now I'm expecting at the third packet, which is sequence number 3, once this poll being transmitted without any poll, without any feedback coming back, reaches and exceeds. Once it reaches and exceeds, polling is triggered. See now, polling will be triggered. Poll bet 1 equal 1. This means now the GNB is requesting the UE, transmitter requesting receiver to send the feedback. So in this case, once 1 is being sent, the T-ball retransmit timer will be starting. And in case if no feedback received at all within this timer, all of this will be retransmitted again. I'll explain this one also in a different example. So now you can see, now that once the receiver received poll bit number 1, it's sending now, okay, now this acknowledgement for these 3 sequence, as you can see here. And in this case, also at this particular area, suppose that the T status perhaps timer would be starting as well. I forgot to add it here, but this will be starting that I cannot send any other additional feedback until this timer expires, which is 10 milliseconds. Okay, yeah, it started here as you can see here, and the T-ball retransmit timer will be stopped in any cases. It will be stopped when there is a feedback being received, whether it's acknowledgement or non-acknowledgement. And if it's expired without receiving any feedback, so the retransmission will happen for these packets. Now let's move forward. This is the second example. It's exactly the same, but I was here speaking about the poll BDU. Now let's speaking about poll byte, and both of them doing the same function, which is mainly defining when the transmitter will decide to request from the receiver to send the RSC status report or a status BDU. So this here, assuming you have poll byte is 200 bytes. So this means the total number of traffic or bytes within a poll will be 200. And here, assuming that the first packet being sent was the size of this packet to RLCBD was 100 byte, the second was 100 byte. Since both of them is equal to 200, which is this one, then here it will be requesting, as you can see, 1. So here the receiver again will be sending the feedback with acknowledgement for sequence number 3. And together they ensure this together, poll BDU and poll byte, ensure there's efficient flow control and feedback mechanism in general. Okay, so this was explaining the first 2 parameters, which is poll BDU, poll byte. Also, we give explanation about the T-ball retransmit and T-status prohib. I'll give for the others also within the retransmission example. Now let's move forward for the example of the retransmission, which will be giving a very clear image as well. Okay, here for this example, I'm explaining 2 different examples, and this will be mainly covering the T-ball retransmit and the maximum RLC threshold, maximum number of RLC retransmission, and the T status parameter as well. So here in this example, in the scenario 1 or example 1, I'm assuming here there will be a retransmission for the RLC retransmission due to non-acknowledgement being received from the receiver side. So for a specific RLC, for example here, sequence number 1. So let's see what we have. So initially, as you can see here, the first initially transmitter or GNB transmitted sequence number 0 with poll bit 0. It's not requiring any feedback from the UE yet. Then again, sequence number 1. This is the one which is going to be lost. So it's saying poll bit still 0. So it still didn't request any feedback from the UE. Then it sends sequence number 2 within the poll. So the poll bit was 1. Then he now is waiting for a feedback from the UE. Again, the T-poll retransmit will be starting once this one is set to 1. And now there is a feedback coming from the UE, RLC status BDU, telling him this acknowledgement sequence number 3. I'm waiting for sequence number 3, which is after 2, but not acknowledging sequence number 1. I received 0 and 2, and I'm waiting for 3, but I have a problem in sequence number 1, and this non-acknowledgement, please retransmit it again. So in this case, what will happen? This timer, it will start and stop once you have a feedback. So since you have a feedback here, this one will be stopped, as you can see here. And again, the T-status perhaps timer will be starting whenever there is a feedback sent from the UE, and the UE cannot send any additional feedback until this one is expired. So the very longer of this timer, it can delay the feedback from the UE. The very short one can increase excessive feedback from the UE. So now what will happen? We're expecting that now sequence number one will be retransmitted from the unit B or the transmitter because it received non-acknowledgement here. And assuming that this one is being successfully received and the UE is gone. UE replied for that or receiver replied for that one. Now for this one, this one will be for the maximum whenever the maximum transmission threshold is going to be reached. Here, scenario this one, I'm assuming that retransmission RLF radio link failure being triggered due to T-ball retransmit timer. This one expired and maximum threshold, maximum number of RSC being reached. This is assuming now the maximum threshold is 3. Okay, so again, let's move forward. Here we have sequence number 0, pull bit 1, sending now requesting directly for the feedback. Okay, so the UE send or the receiver send the feedback acknowledgement sequence number 1 or non-acknowledgement, but this is what, sorry, this acknowledgement or whatever feedback is being sent, but somehow to us being lost at not being received by receiver. So in this case, this one was started, but it should be stopped if it's received, but this one is not being received at all. So once the time is being expired, what will happen? You have another timer is being started here, the T-status prohibited, which is prohibiting the user sending additional feedback. So now what will happen? You will find that since the T-ball retransmit expired, then directly after the unit B or the transmitter should send a retransmission for this one because he didn't receive any feedback within this particular time. And the UE cannot send the feedback. It can just send the feedback once this timer is being expired. So now sequence number 0 is being sent, retransmitted again, which is this one, with pull bit 1, asking him. Again, the same scenario being repeated for the second time. The UE replied, but somehow the feedback was not received by unit B. The timer again expired, keyboard retransmit timer. Again, retransmission happened. For the third time, again, this is happening now. It's being transmitted, not acknowledgement. So in this case, what will happen? As you can see, for the third time, we have 1, 2, 3. So this means the maximum RLC transmission being reached now. So in this case, unit B will declare there is a radio link failure because the user couldn't correctly decode all the retransmission. So now the maximum transmission threshold being reached. So the radio link failure will be triggered in this case. Now let's move to the, I think will be one of the last parameters for this part, which is related for the RLC, which is related to TRA assembly, how it's being working, and so on. Okay, if you remember in the very beginning, I mentioned something related to the TRA assembly timer, and this is usually at the receiver side. At the receiver, always remember reassembly. Reassembly means I'm trying to recollect something, right? So if there is a segmentation, only in case of segmentation for the RLC from the transmitter, the RLC is being segmented. In this case, the receiver should do a reassembly, but it should do it within a specific timer. And if this timer is expired within doing the reassembly, the receiver now would be requesting or be sending the status report, which is telling them, for example, I didn't receive this and that. Let's see with an example. The first example, number 1 here, this is assuming all the transmission was being successfully received, all the success of the RLC segments, okay? I'm assuming for sure this is a segmented RLC. So as you can see for this example, here, initially, the unit B or the transmitter sent data with sequence number 0, size 100 byte, okay? This was the first one. Then the second segment, DCI 1, which is means data, sequence number 1. This was a complete one. It was not segmented. Then the second one was being sent here. The first segment sent here, you can see here, it's saying sequence number 1 and segment information 01. Segment information 01, as you can see in the top right here, this means the first segment. Once the UE or the receiver received this information with sequence number 1 and it's having this header sequence information 01, it will know that this sequence number 1 data is being segmented. So it needs to start now the TRA assembly timer. It will start the assembly timer and it will be waiting for the additional or the remaining segments for this segmented one. Once it's received within the timer, the last segment, which is 10 here, as you can see for that part, now this means it's being completely received everything, so it will stop the timer. So once if all the segments being received within the timer, so there is no problem. It will stop the timer once it receives this one. Then it will send directly after the since this poll flag 1, so it will send the feedback acknowledgement sequence number 2. I received 0 and 1 completely. Now I'm waiting for the next one, which is 2. So here again, the transmitter requested the receiver to send the status report. Okay, RLC status report. Now assuming that there is one RLC segment is being lost, assume that same example here, but here this one is being lost, which is sequence number 1 and 0, which was the last segment, which is last segment here. So here the timer is being started. So it will keep waiting for this timer. So once the timer expires before receiving this segment one, so in this case, the receiver himself will send RSC status BDU report telling him after this expiry of the T reassembly, after the expiry without receiving this one, the receiver will send directly telling him, I didn't receive this one. I did receive non-acknowledgement of sequence number 1. I just acknowledged the first one with 610, but I received this one. I didn't receive. Please retransmit it again. So the GNB or the transmitter will be retransmitting again DCI1 sequence number 1. Again, those will be transmitted for the one which is not being acknowledgement here, which is this particular area. So the main idea here for the reassembly, it's a timer to wait for the segmented RLC to be received at the receiver side. And in case if it's expired without receiving those timers, without receiving all the segments, that the receiver himself will be sending a status report telling him, I didn't receive all the segments, please send it now to me. This is the main idea of the assembly. Now, the next section, I will just quickly show you how you can check this kind of information from the DT logs, drive test logs. Then we'll be jumping into the relation between the MAC and RLC for the timer's point of view, which is also very critical one to understand. Okay, here just as you can see, this is just showing examples from the RLC timers and parameters and the drive test logs. You can see, for example, here, again, if you remember, during the RLC setup, connection request, connection setup, you will not have any, like it will be using this RB0, signal reader B0, transparent mode. So you don't need any timers, right? You will start receiving the timers starting from the RSC connection setup. You can find it RSC connection setup or even the self configuration group message from the 5 standalone. Because why? Now, after you pass the SRB0, which is during the RRC request RRC setup, once you receive the RRC setup, now the next for SRB1, it needs to be based on acknowledgement mode. So you are expected to receive the SRB1 within the RRC setup message or even the serial configuration. You can see, for example, 4G and 5G on standalone, I have seen this one, an RRC connection setup. This one I have seen this message which is called cell group configuration and all. You can see here, this is the timers at the uplink direction and this is the downlink direction. Again, this is from the EU perspective. You have the same timers from the GNB itself, but you can see because it's configured at the GNB. So you have this downlink means this is whenever you're going to receive data, you will act, the UE will be acting as a receiver. So this will be his timer. Reassembly is 40 milliseconds, status provided 0 millisecond, and this is a sequence number 12. Usually the sequence number is less for the signal distributor and is 18 for the data distributor. And those one for the transmitter, you can see sequence number, T-polar transmitter, whenever he acting as a transmitter. Same again here, you can see for the data distributor, this is usually you will receive it afterwards once you complete the RRC. Once you get a new RRC configuration message here, you will find your data distributor as you can see here. For example, this data distributor number 1. You have here the sequence number, also transmitter and receiver, the assembly timers, and T-status prohibit. And also you can see, for example, sequence number is 18 here for that example. So this is how you can check. Also from the same message within the RLC setup, you will find the HARC process. For example, this is telling you have 16 HARC processes here, which is also can be used for your calculation to define how many HARC you have processed in the configuration. Let's now move to the last part for the retransmission and the alignment between RLC and MAC timers. Okay, this very long example is just showing you what is the relation between the TRA assembly and the HARC retransmission. TRA assembly, as we highlighted in the previous section, it's working in the RLC receiver or the receiver as in the receiver side of during the RLC part, usually during the segmentation. HARC is the thereafter during the HARC transmission. So what is the relation between both of them? So I give an example in texting here. You can just quote it from the left side here, and this is a visualized example. Okay. So let me explain what we have. So in this example, I'm giving two examples. The first one, I'm assuming the TRA assembly is less than the HARC time, and the second one, I'm assuming the TRA assembly is greater than or equal to the HARC time. So let's zoom in the first example first here. So in this example, as you can see, I'm dividing this into two parts here, and we have a color code on the top side here. We have the RLC layer and we have the MAC layer. So I'm assuming here you have one bucket being segmented, as you can see, into four buckets. Okay, so we have sequence number one being segmented into four buckets, being segmented. And green color means received. This color means it's lost. This color red means there is a hierarchy transmission. So we have the RLC layer and MAC layer. So assuming now at the RLC side, the first bucket sequence number one, which is having segment information 10, segment information 10 means this is the first segmented packet being received at the RLC. So directly the TRIO assembly will be started once we have this packet being received. Then within the timer, this is expiry. This is timer will be expired here. This is the duration of this timer. Within the timer, the receiver received sequence 1011. Then directly he received 10, and he was expecting to receive still one packet in between here, but he didn't receive it. He received the last one here. Okay, he found that the bytes it's not following the sequence. So here, what will happen during that time? The HARC will try. This packet might be lost in the air interface. So there will be a hierarchy transmission. So assume now your maximum hierarchy transmission is 8, okay? And assume this is the time which takes for the hierarchy transmission. Just for this is might be started here by the way, but assume you have a maximum hierarchy retransmission. So the first one was failed, second one was failed. You have 8 attempts. Third was failed, fourth was failed, fifth until 7 was all failed. Just at number 8, this was being successfully received, and it was being able by the HARC to successfully recover this data. So it will now send this one with the missing information, sequence number 1, which was being lost here. So it will be resending here. But unfortunately, it's being sent after the reassembly timer being expired. This means the HARC was being unuseless in this case because already once this timer is expired, the RLC retransmission will start because the RLC or receiver will be sending, I didn't receive that watt for the transmitter, please retransmit again. So that's the case. So in this case, what will happen once you receive that? This means this is useless because it's coming out of the reassembly. This means the RLC receiver already sent to the transmitter telling him, I didn't receive from the RLC perspective because please retransmit it again. Now let's go to the second example, which is the bottom down here. Assume the reassembly timer is greater than the HARC time. So assume the HARC time is here or whatever. Okay. And now the same example, this one was being lost. And as you can see, RLC segment, this one being lost initially. Then it was being sent here for the receiver. Since he received it here, this means he will being able to recover the lost one because the HARC was being able to successfully decode this data. So this is the main idea that whenever, for example, assume that you have a plan in your network to extend the maximum HARC retransmission from 8 to 16, because I think in 5G it's supporting up to 16. So, and assume the time of the HARC round trip time for DDNR, for example, is 8 milliseconds. So this requires you need 16 multiplied by 8. This would be your timer for reassembly, minimum time for reassembly, to be able to wait for the recovery from the HARC, maximum HARC transmission. And I have give some written example in the left figure here. So in this case, you need to ensure that the reassembly is at least greater than or equal to the HARC. Try to make it at least slightly, because again, if you extend it, you have a very large value or very long value. This also can result in a very long delay if you keep waiting for longer time and you didn't allow the RLC to take the retransmission. This can also increase the delay, so you need to be very careful whenever you tune this particular timer. And one important point to highlight, for this is for the AM mode. For the UM mode, for example, you're using voice over NR or VoLTE. Usually this timer is set for very high value, because at the end, in the UM mode, we don't have RLC transmission, right? So you need to give the voice over NR or VoLTE mainly relying on the HARC transmission. So you need to ensure 100% the HARC is being completed. Because at the end, if you didn't ensure that, the time will be expired, this will be triggered as lost. It will be counted as a packet loss. So that's why you find that, for example, voice over NR, VoLTE, or even video services will have a longer time for that one compared to the data, because there is no chance to have a receiver transmission. Now let's move forward to the next part and last part about the retransmission. The last part here, it's about the comparison or the relation, in other words, between the TPO retransmit and the HARC maximum Hark retransmission. Okay, what is the relation between both of them? But let's first tell you. Usually, the vendors is doing this T-ball retransmit as a dynamic way, so they are increasing dynamically. Yes, you have a start value, but usually it's like dynamic. But anyway, let me explain what we have. So here we assume that we have this one. Here I'm assuming that the maximum Hark time is required 40 milliseconds for the Hark transmission. Okay, 40 milliseconds. And the first example here, I'm assuming that T-ball retransmit is set at 30 milliseconds. As we highlighted before, T-ball retransmit will start once the receiver sent a feedback with pulpit 1 requesting the UE to send or the receiver to send the feedback about that part. So now let's take it one by one to try to see what we have. So assume now the first sequence number 0 is being sent with pulpit equal number 1 from the RLC layer for at the transmitter side to the MAC layer at the also the still at the JNB side. So here the T-ball retransmit, which is this timer, started, which is starting from here, ending here at 30 milliseconds. So now what will happen? Sequence number 0 is being sent from the JNB MAC to the receiver MAC at the UE side, okay, through the air interface. So that's being received here as sequence number 0. So somehow this packet is being lost, sequence number 0. So what will happen? The MAC layer will try to recover the data before going to the RLC retransmission. So you have maximum number of Hark will be trying to do it. Here you have here the first Hark retransmission being done at U1, then it was failed, then again second one being retransmitted again. Then the timer of the T-ball retransmitted was being expired here before receiving the maximum number of Hark. For example, assume you have here 3 maximum Hark retransmission, 1, 2, 3, all of them, the first 2 was being failed. So what will happen since this timer expired before the Hark completed the complete Hark process, the RLC will be requesting, sending here directly after the expiry, a new RLC sequence with retransmission for the RLC from the RLC side. So this will interrupt the Hark processes here, okay? So now, assume now you extended the timer for the T-ball retransmit to become as 50 milliseconds. So instead of expiring here, it will be expiring in the bottom down here. So this will be start and end point. So in this case, you will allow the third Hark to be completed, which is that part. So in this case, here the retransmission was being successfully, and this data was being transferred successfully from the MAC RLC to here. So in this case, there is an acknowledgement. So you don't need again to go to the second RLC retransmission because the Hark already recovered that part. So the takeaway from here that the T-ball retransmit should be greater than the MAC retransmission time, round trip time, to ensure the Hark time is not being the Hark retransmission is not being interrupted by the RLC. And the T-ball should ensure that all the Hark processes is taking effect. That's it. That's all about the RLC retransmission. Now let's go to the next part about the differences between 4G and 5G. Here, just quickly recap the difference in case if you don't know about it between the RLC and 4G functionality. Okay, retransmission supported by both of them, no change. Segmentation reassembly also by both of them, duplication detection by both of them. But the very important part here, very important part, it's related to the reordering. And the 4G, before the reordering, you will find timers as a reordering was on the 4G at the receiver side. Means that if the RLC receiver received a packet out of sequence, for example, he was waiting for 1, 2, 3, received 1, then 3, the RLC will not forward any packets to the upper layer until he receives the right sequence. This will cause a lot of delay because he's keeping the packets in the buffer, not forwarding, so it can impact the buffer. It can impact as well the latency. So they have removed this function from the RLC and they moved it up to the BTCP layer. Now you have reordering at the BTCP layer. So this can improve the latency and also can improve the RLC buffer from the perspective of 5G. Concatenation as well was being also done before at the 4G RLC. Now it's not being supported by the 5G RLC. As you can see here from this image, there is a segmentation supported by both of them. But before, for example, if at the 4G side, before it was doing kind of, it can do additional concatenation into one RLC BDU. But now in the 5G, no, it cannot do that. Once the data is here, it will just directly send it to RLC BDU. There is no concatenation, and also this can be reflected in the latency. The last part here about the sequence number, which we already explained, the maximum sequence number was 10 to 16, while here 12 to 18. 10 to 16 or 10 to 15, I don't remember. but I think 16. Then this one will 12 to 18. As I highlighted, higher sequence numbers means we'll have a higher window size, means you can support higher throughput rates, and this is more logic when you're speaking about the 5G, because in 5G you are higher data throughput, as we highlighted in the part related to the transmission windows advancement. The very end part, for that part, it's related to the RLC variables. We have multiple variables at the transmitter and receiver. I have just summarized it here in this table, something called TX next, RX next driver, and so on. I will be sharing, if you are interested to know about that part. This already explained in an indirect way in our on our images. But if you need to know the exact definition, I have added here, and also I will be sharing one good link, which showing the visualization example for that part. And that's it for the RLC session. I know the session is very long, takes 1 hour and a half. I didn't expect that. But I believe, I hope if you like the session to share it and to spread the word and to press like and share it with your friends, and keep waiting, or stay tuned for next one about the BDCB and TCB. Then we'll be moving to the Mac and including the possible cases of the packet losses in general. Thank you very much, and see you next video.